Looking now at the efficiency of the previously fabricated solar charging setup, and this is going to be a fairly, fully theoretical video, so pre-warned, it will be boring. It will probably lose most people, so feel free to skim or just pass over. The objectives here is to look at identify the conditions under which we did this and try to identify what was the incoming power, what we got, and eventually what efficiency we got. And basically just some basic calculations along the way and getting down now to what it was all intended to do, which is charge a cell phone. I want to clearly note this is rough calculations and assumptions. In some cases the information are from unverified websites and third-party sources. Feel free to look at them. I did credit them. If you don't like them, don't take what you get here. This presentation wasn't really cross-checked, so they're subject to errors. If you find any, there's a comment section. Note them. I'll look at them. Hopefully they can be corrected somewhere down there, or I'll have to do a follow-up. Okay, getting into the basic concepts of solar. The sun moves across the sky during the day. Let's go with the concept of moving across the sky. It's just easier. From our point of reference, it moves. It doesn't really move. We move, but yeah. Anyway, sun moves across the sky during the day. The position of the sun actually changes throughout the year. So if we were to look at the sun, let's say 12 o'clock in the day, and we would look at it in January, it would be different in probably March, going on the road, middle of the year, autumn, and quite down December would be closer to where it was in January. It makes something called an analemma. That is the shape. That picture was extracted from Wikipedia, as you could see. The basic energy concepts here now we're going to get into is that your solar energy that you get is based on three components: a direct, a diffuse, and a reflected component. And the combination is what really is your total energy that the solar panel sees. DNI is the direct normal irradiance, and GHI is the global horizontal irradiance. And based upon solar GIS, I was able to get some values for this location at 1600 and 2000. This is based upon colors and watching a map and picking colors, so yes, subject to at least a 10% error there. The direct component, right, what you need is actually to work out the angle of the sun in relation to the angle of the panel. Now there's some interesting concepts here which I can't really cover in this video, so it gets too long. But there's the azimuth of the sun, which is basically the angle measured from north in a circle clockwise. The elevation, which is above the plane of reference going upwards. And the same occurs for the panel and the elevation of the panel. These are the four things you really need to ascertain how one relates to the other. NOAA website has decent information on this, and I used their website. I cross-checked with another, it was close, so let's just go with their figures. The date of reference was the 8th of January, that's when these tests were done, 2018, and 2 p.m. 1400 military time. Azimuth angle of the sun, AS, was 220 degrees according to them. The azimuth, the altitude angle, elevation basically of the sun was 47 degrees. The panel information is based upon what I have set up, and the azimuth of the solar panel was basically facing south, almost perfectly facing south, so 180 degrees, and the panel was at 30 degrees to the horizontal. Going with this long formula, let's not get into it too much. Pause if you want to read it, but you don't. Most likely you don't. Anyway, and getting back now to the direct component, we see that it's about 81.2% of the normal incident radiation. Subbing the values that we previously discussed, that is 1309 kilowatt hour per meter squared. jump into the diffuse component now, and we're using the simplest model, which is the isotropic sky model, and that's basically just saying we are going to look at the portion of the sphere, well, half of a sphere, because it's cut on a plane, that if a panel is at an angle, it could see, and essentially cut off the piece of the sphere that isn't being used. At 30 degrees, we obviously aren't that high up, so our cutoff is about 93% is visible. The that's what 6.7% not visible. So that's the sky view factor, and essentially using the previous value for the GHI, we get a global irradiance diffuse component of 1866. Getting now to the reflective component, the panel was placed on a galvanized roof. It was sloped. That has not really been taken into account, neglecting that. And there are one tree around wall. There's some other little slight environmental factors that were not actually considered. Anyway, getting on to the reflective properties of the galvanized, that the alpha of the galvanized is 0.35. It's really actually quite small. When you to check that formula out, it comes at 2.3%. So even if this is actually wrong, it's not going to really change the answer to any significance. This is reflective component is practically negligible as it stands, and being 46 compared to the other two. Next slide here, we have the total value for the module: direct, diffuse, reflective. 1309, 1866, 46, 3221 kilowatts per meter squared. Now let's get to the actual. Now this is how much is coming per meter squared. These panels aren't even a meter, right? So width of the panel, length of the panel, area of the panel, and when we multiply the area by this, we see that basically 188.4 kilowatt hours. If we divide out and bring that into seconds, we would end up with about 52.3 watts. And this is the maximum power that this panel could ever get if it was 100% efficient in that orientation, at this location, at the noted time, and the date. And of course, no clouds, no weather, no other conditions that would cause that problem. So that's the maximum we get. Grabbing that value now, and let's have a look at what the manufacturer says. 7.5 watts. Based upon maximum efficiency that the manufacturer says, that's 14.3%. And that is actually well within the capability of polysilicon cell. So, they're not making unfair claims that, cannot be achieved in reality. Anyway, what we really got from our estimation last time was 5.92 watts. And based upon that, we're getting 11.3%. Sounds closer to what we would expect. Not that far apart anyway. And really, what we actually got at our battery charging, our real actual measurements, not what we calculated could be our best, which is the MPP, we got 5 watts, and that's 9.6% efficient. And yeah, that sounds about right on what I'll get. So notes here on what we've done. We've looked at everything, but we have not really considered that a large amount of this panel is not actually silicon. There's contacts in there, there's extra spaces that are on borders and things that they've left out. So silicon area, when on the side of question of 70%, the actual silicon cells themselves may be 1.4 times as efficient as the overall panel, simply because 70% of the panel might be covered with silicon, the rest non-producing. It does not produce power. Of course, anything light that falls here is wasted. The next thing to note is that this is a hobby level panel from China, and China is very well known for not being giving you a highly efficient device. So yes, it will not be a grade A panel, which is 100% of work. It would be a grade B, which is 90% work. It's probably a grade C, somewhere between the 75 and 90% of its cells functional. It could be worse. So Yes, there is, there's it's not going to be the best panel in the world, that's for sure, right? And then no consideration was made for losses in the wire, but I don't think it's necessary. To be honest, it's a 18 AWG 18 wire, and the current is less than 0.4 amps. At that low current, losses are negligible. Voltage drops and that is negligible. Having a look at a graph of the direct radiation, courtesy PEducation.org, we can see at the location just after 6 a.m. is when you see sunrise, just before 6 p.m. is when you see sunset. This is for the illustrated day, and we can see it's just over 1 kilowatt per meter squared, just over the 1000. That is the benchmark that people work with. So that gives us a good idea of how the sun looks at this location. No funny business, no late nights close to the equator. This graph shows the direct radiation in kilowatts per meter squared per day over a year. So essentially, this is the year from day 0, January, to day 365, and this is the radiation that you would get on, right, in terms of per kilowatt per meter squared. So essentially, our 1000, we're getting, let's say, 8.7, 8.6 hours, sun hours, going up to, let's say, 10, right? That's the blue, incident power, right? Power on the horizontal, power on the module. Again, they made assumptions, so let's not use this, but the blue one is really the most important. We are seeing practically 8.6, so let's say 10. That's the number of sun hours we're working with. This third graph shows the direct radiation, and essentially, again, this is a year, and this is the number of hours, sunlight hours, and we see it doesn't vary very much from 6 a.m. very slightly. It doesn't vary much in terms of the number of hours in a day, right? This is 11.7, but this is not sun hours. This is just hours of sunlight, not what you consider sun hours, which is an integration of the first curve, the area underneath, in terms of it normalizing it to 1000 watts per square meter. And this is just sunset again, doesn't vary much. Close to the equator, things don't move too much down here. Power calculations. Based on our previous graphs, right, we're looking at the 9 sun hours, right, conservatively, because it was between 8.6 and 10. And we're saying that our power, actual power that we measured, was 5 watts. So let's say this is what we're going to use for our calculations. Now, in reality, this isn't really applicable. This panel was perfectly clean. It was at a decent angle at a good time of the day. Yeah, it isn't exactly a good answer to work with perfectly, but let's simplify our lives and just work with the 5. The thing about it is also the efficiency, and this is wrong, spelled wrongly. The efficiency, and that's the power drop. The power will drop off rapidly as the battery charges. That's because the voltage will drift closer to the open circuit voltage. And if you recall, the efficiency curve with respect to the MPP, as we drift above 12.24, very quickly the efficiency drops off. So this efficiency will go very quickly. The potential energy from the panels, 9 hours by 5 watts, maximum potential energy practically 45 watt hours. Our car battery is 80 ampere hours, and that's new, but let's work with new values. Say nominal voltage is 13.2, because those cells tend to be about 2.2 volts, right? That's 1056 watt hours. Now I'm saying it will take 23.5 days to charge this battery from completely drained to full. That is not really a realistic situation. You can't take a completely dead battery, you can't charge it to full with this. What I'm trying to show here is the great variation between what we're getting in one day and what the battery capacity is. So basically, if we have some bad days, the battery has more than enough capacity to ride it out, rally out, maybe even a week without great problems. And when you have a good week, it charges back up. Jumping now into the power calculations again, moving a little further into the power calculations. right? Let's have a look at our typical smartphone battery, because our intention was to actually use this device to charge a single smartphone. That was really the plan at the end of the day. One charge at a night. So a typical smartphone battery is about 6.5 watt hours to 11 watt hours. Right, that's the Samsung S8. So currently on the market, probably a good benchmark. Power from the battery at very best turned out to be 45 watts, which we got from before. If we had overcast size, we noticed that the power was 1/3, and that was in the previous video. We looked at what we got in terms of current. So that will give us 15 watt hours. Solarfacts.com states that a lead acid battery in solar systems is generally 85% efficient. That's what you assume. Let's go with that. Let's not try to tweak it too much. I'm sure they know what they're talking about. And so our battery at best now is going to get 85% of that, which is 38.25 or 12.75 on a bad day. Right? This is a 13 volt battery, right? And a phone needs 5 volts DC, so we have to get into DC-DC conversion to actually get our 5 volts. So let's jump into that, because that has a different efficiency altogether. Our options in terms of conversion is a linear regulator or buck converter. The linear regulators, what essentially it is, it's a voltage divider. Essentially it's like a resistor network. So basically part of the voltage is split over one side and part is split over the other side, and one of the pieces legs is what you want. So the 5 volts will be on one side, and then it'll be 8.2 volts on the other side to get us at 13.2 volts there. Essentially V out over V in is the efficiency, and that means it's highly inefficient when the voltage that you're putting in is significantly and higher from the voltage out, and a linear regulator always does higher to lower. And efficiency at 38% means that, well, we're going to get about 14.46 watt hours, and in our worst case day 4.82. There's a high possibility that this system will not generate back the power it requires on a bad day. The thing is, the good day isn't that far above. While the battery has the extra store capacity to be able to rally us, it isn't that far above what we may be pulling. So it doesn't have the system. This linear regulator is killing all our power essentially. We are losing too much power. So second option is a buck converter. Essentially, it takes a high. Now there's buck and boost converters. This one takes a high to low, boost goes low to high, as the word goes, boosted. These typically have an efficiency of over 90%, but I bought an El Cheapo off of eBay and it's listed at 80%. Let's use that value. That's a reasonable price item. Let's work with the reasonable price ones, not having the 92, 93, 95% that are claimed. The power conversion using our 80%, it gets us at 30.6 watt hours on our best day and 10.2 watt hours on our worst day. This is very close to our upper limit, and this is way higher. So in case anything goes wrong, this battery, if it does not get its charge for 1 or 2 days, it's going to slip slightly, and one good day and it's going to charge back up. So our solution of using a buck converter works. The entire system will work based upon the parameters we set out. This can actually charge a single phone, deliver you 1 charge per night comfortably. Obviously, with something being this high, we could get more than 1 charge in there, 2 to 3 charges. But let's say comfortably, what we set out to do was design a system that could do 1 charge on a high-end phone per night. We didn't know the end result before we started. In fact, before all of this conversion, of course, by the last one, we were suspected that yes, we had the power in there. But before all of this the maths was worked out, it was not known. Now that we've done all the maths, we've looked at our worst case, our best case, and we've seen that using a buck converter, we can in fact meet our objective. With all those calculations and numbers floating around, it might not be obvious how little energy that was common incident on this panel actually got to be useful in the end. So let's just look back quickly. The efficiency of CapGen we worked out to be 9.6%. The efficiency of the battery we assumed to be 85%. The efficiency of the DC-DC conversion used 80%. Overall efficiency of this entire thing is 6.5%. So it's not that efficient. It's actually pretty bad. If we take a snapshot of our maximum power, a little time back we talked about 52.3 watts. We're already getting 3.4 watts of useful power at the end at the plug to our phone, and that's really not that much at all when you consider 52 watts, 3.4 watts. So that's what the numbers at the end of the day help you visualize really what you're working with.